So what I'm going to do today, we're going to jump into the lecture immediately. So based on what I have seen in OOP344 and questions that we went through, I see a major problem with understanding what pointers are and how do we deal with them. So I have a lecture from my IPC 144 era that I taught pointers. So I'm going to go through that, yes.
I was going to ask about workshop 0.
Pardon me?
I was going to ask about workshop 0.
Okay, go ahead.
Does it need to be done by the end of this class? Or?
No. Workshops are not like OP244 anymore. They're all open. You can submit them anywhere you want, anytime you want. Okay? Check what is the due date. If the due date is today, if extension is needed, I'll make it more. Okay, it doesn't matter. Submission for is assignments. Any of the assignments up yet? Have you seen anything? Anyway, so if they're up, then I'll set those things up so you can actually.
But it's still true from matrix?
Pardon me?
Is it still true for matrix?
Yes.
Professor,
Yes.
we finished lab 0, so assuming you're still working on lab 1?
Lab 0 is, lab 0 is lab. The rest is assignment. There is no lab.
Should we work on assignment 1 then?
If it's up on the thing, you start working on it. Sure, no problem. It's up now?
I'll check.
Yeah, anyways, if it's up, I don't know, because I asked someone else to put them up. There are no team leads anymore. So,
Yeah, is the training?
no. It's a long story. Ask me later. I'll explain.
If it's not up, what should we be doing?
Yeah, so if it's not up, let's continue our studying. As soon as it comes up, then I'll let you know. So, okay, I'm going to have a posting on it, so don't worry about it. So, our job is to first completely, clearly understand what pointers are, because we're going to have lots of memory stuff to do, and I want us to understand exactly how things work. That's why when I start the lecture about pointers, what I want to ask you to do is format your brains about knowledge of pointers, as if you want to start fresh, and we'll continue after that, okay? So, as usual, I'm going to create a new project. And I'm going to stop doing that, hopefully, I don't know, from a session or two after that. I'm not going to do this anymore. I usually do it the first couple of times, and then we'll stop. So NAA, and we are 03, September 12th. Create. And copy. Okay, so as usual, create a new item, prg.cpp, and set the property to set the property of the project to have the C++ 20 standards. Apply and OK. Test it. And using namespace std, return 0, and we're going to have cout 03 September 12th, OOP345 NAA. Compile and run, make sure everything is set up properly, and then we start. Okay, yeah, everything's good. Okay, I'm just going to add one more thing over here. Let me just set this thing up. This one as A, hello, CPP. Create a new one and let the games begin. Okay. All right. So let's start. Again, fresh minds. We want to start from scratch as if we are, I think I can't bring this up, can I? Is it going to block your, definitely it's going to block your view. Let me bring it down there. So, that's your RAM, the computer memory that you have. And in your RAM, what you have is that you have you have series of bytes in your computer. How do we create a byte in C language?
A byte, I guess instantiating a variable? Or a
Yeah, which variable represents a byte?
int or...
No, int is 4 bytes. Which variable is a byte in C language? You create 1 byte, pass it through. 1 byte.
So it will be a
Seriously? You don't know what is 1 byte in C language? A character. Shame. Shame on you. You're in third semester. 1 character is 1 byte in C language. Okay, we don't have anything called character in C. I can just keep it. We don't have anything called character in C. Character is simply an integer that has 1 byte length. Goes from 0 to 255 or minus 128 to 127. When you actually print a character type, you're asking the graphics card of your computer to print the shape of ASCII code of the thing that you have inside the character. We're clear on that? Okay. So that's our memory. Each one is 1 byte, 1 character. It starts from 0. So the index of the memory starts from 0 and goes up to the amount of money you have in your pocket, which means how much RAM you have in your computer, right? So the more the RAM, the bigger the address is. So to kind of demonstrate, to be able to show you what we're dealing with over here, as you see at the beginning, I'm saying start, then I'm over there, I'm putting 23,100. I'm putting that thing. That's we assume is the addresses of that part of the memory. But just to simplify it, what I'm doing, I'm only putting the right 3 digits. So 100, 101, 102, 103, 104. We good? That's your RAM. And the index of the byte in memory, character in memory, we call that address. So essentially, when we say address of a byte in memory, that's essentially the index of that byte in your RAM. Okay? We good down to this point? Are we okay? There's nothing mystery about it. So when I say what is sitting in is address 110, it means go to the index 110 and see what's inside. We good? All right. So when you write in your program something like int var, what happens is that your compiler and operating system, let's call it the system assigns a piece of memory relative to the type that you have. And that's essentially, we said, the definition of a type in a language. So when I say int represents 4 bytes in memory. So what it does, it occupies 4 bytes in memory and names it var. So whenever you set var to something, those 4 bytes will be set to memory. What is the address of var? What is the address of var now?
Oh, it's 108.
108 is the address of var, right? Where it begins, that's where the address is. Are we okay with this? Are we all okay with this?
Yeah.
All right. So essentially, when I create a double, because double represents 8 bytes, then 8 bytes somewhere in memory is going to be set, and it's going to be tagged as the value that I'm calling it over here, dvar. We good with this? All right. So this is good. It's all good. So when you create a variable has a name, you can put stuff in it. So I don't know, if I set that var to something, the value is going to go and overwrite the whole 4 bytes, because integer is 4 bytes, right? And when I put something in a double, it's going to happen like that. Are we good with this? Questions? All right. So, what's your name?
Javad.
Javar?
Javad.
Javar.
With the D at that.
Javad?
No, Javad.
Javad, okay, okay. In my language, we say simply Javad. It's okay. Javad, okay. Okay, so Javad is here. So if I say, Javad, can I have that mouse? Javad is here, he gives me the mouse, right? Because he is in my scope, right? But if John is in the other classroom, and I want the mouse that John has, then I cannot say, John, give me the mouse, because he's not here. His scope is somewhere else. So I have to tell to Javad, go to room yada yada, give the address of John and say, go over there on a 3rd table, some guy sitting over there, get the mouse and bring it over here. Are we okay with this? So when the variables are not in the same scope as ours, we need their addresses to be remotely do something with it, right? So we know we need an integer because we need numbers to do things, right? We need a double, we need numbers to do something. So we need some kind of a variable to hold this address in case we want to deal with something remotely. And our job today is to design that ourselves. Let's assume C doesn't have it, and we want to design it ourselves. If I want to design a variable, some type of variable, to hold an address in, how many bytes it's supposed to be?
At least 1. At least 1.
It cannot be 1. If it's 1, it's 250, 255. It's just, your memory will be 255 characters. That's very small. So in a 32-bit compiler, it's an integer. That's as big as, so 2 to power 32. And obviously, it's not going to be a negative value. You don't have address minus 52, right? So let's design our type and call it a pointer. And we say when we create a pointer, PTR, it's going to occupy 4 spaces. You see the green thing at the top? Okay, so PTR is a pointer who occupies 4 bytes. What is the difference between PTR and var? Var holds an integer. PTR is holding kind of an integer, but it's a positive number that is supposed to be address of something. That's why we kind of make it different than a regular integer.
Can you repeat it now?
Pardon me?
LCT number?
It's a positive number.
Can you, well, that you can add something?
You can add something to it, yeah. You mean add something to a pointer?
Yeah.
Of course you can.
No, that's what you said. So I didn't get it.
So yeah, a pointer is simply an integer that cannot be negative. And we're going to see that we need some more stuff about it. So we call it pointer PTR, okay? So essentially, if I put something in PTR, let's say 102, okay? What I mean by that, because PTR's job is to hold the address of other variables, is to actually that thing pointing to the address 102. Are we clear on that? That's how we are designing it. But that doesn't make sense. Because 102, nothing is there. It's like, I'm telling you, go to room 5000. We don't have such a thing at Seneca, okay? That doesn't make sense. So it's always better to put something that is address of an actual thing. Therefore, now PTR is pointing to var, right? Right? But when you are writing a program, you create a variable, all you have is the variable's name. You don't know where it is in memory. So we need to add an operation to our language to be able to extract the address of stuff. Let's make it easy. We call it address of. Okay? So, because we are designing the language, we can do anything. So instead of writing 108, I'm going to write PTR is equal to address of var. So address of is an operation that extracts the address of a variable. Are we okay with this?
Can we use pointer equal to 1?
Pardon me?
Do we have to add the address of?
Yes.
We can we like pointer?
What did I say at the beginning of the lecture? I said format your brain as if you have no idea what a pointer is and we want to design one. So if you think about your knowledge from pointers, then you're going to ruin the lecture. No. It's literally address of. So we are designing it. So you have to write PTR is equal to address of var for it to point to var. That's what we are designing. Use your imagination. Okay? Now that we have done this, I have two ways to access the variable. One is through its name, if I'm in the same scope, and the other one is through PTR that is holding its address. But if I put something in PTR, it's going to go to PTR. How can I tell to the compiler that, hey, I don't want to deal with PTR. I want to point to the target of PTR. So let's create that. So I should be able to say target of PTR is equal to 2345. So I created something new. So three things I created. I created a pointer, who's a variable that holds the address. I created an operation, address of, that extracts the address of a variable. I created an operation called target of. So when I put it behind the pointer and I put a value, instead of putting the value in the pointer, it puts it to the target of pointer. Therefore, this happens. Are we okay with this? Right? These are all the tools that we need. So, for example, so now if I print var, obviously 2345 is going to get printed. If I print target of PTR, again 2345 is printed. But if I print the PTR itself, then the address is going to get printed. Are we okay with this? Everything's clear on this? We good? Okay. So now that we have all these beautiful stuff over here, let's try it with other stuff and see what the problem's going to be. I say PTR is address of dvar. Therefore, PTR is pointing to 132, correct? And now I want to say target of PTR is equal to a number. Now let's look at it closely. All the compiler has is pointer PTR, right? Can compiler from this instruction have any idea what PTR is pointing to? No. So it is impossible to accomplish something like this. This cannot be done because it doesn't know what is the size of the target, what it has to set. Our design sucks. We have to fix it. So I cannot just create a pointer in here. I have to tell to the compiler not only it's a pointer, but also tell it what is it going to point to. Therefore, our design should be like this: integer pointer PTR. Now, the compiler knows this PTR is an integer pointer. Its job is to only point to an integer. Therefore, when I do all these good stuff, I set it, it knows the address is integer. If I put an address of double, it's going to tell me what the heck you're doing. You told me integer. Now you are putting an address of double, so it can actually give us errors if we do that. Not only that, when I actually set the target and put the value, it knows how many bytes it has to affect because it knows the target is an integer. Are we good with this? And all the good stuff that we have. Now, if I actually create a double pointer dptr, it's going to be a separate variable. But take a look. The size of the two are the same. A double pointer and an integer pointer they occupy the same size because they are both addresses, right? It's the target size that is different, not the pointer. Because of that, all the pointers have the same size. We good with that? Are we okay with that? All right. So now that we have this one, we can actually do what we wanted to do. Now I can actually say the address, hold the address, target is this, and do all the good stuff that I have done with the other one. Are we good with this? We okay? All right. Let's try it. So I'm going to create an integer value, val, let's call it. We call it val, let's do the same thing, right? Now I'm going to say integer, pointer, PTR. Now I'm going to say PTR is set to target of, oh no, set to address of var, correct? Now I can say target of PTR is equal to 2345, right? Now if I go see out var, if what I said is correct, the outcome will be 3 years later, 4 years later, the outcome will be 2345. Be okay with this? So like this, I can actually do remote stuff with all the things that I have. It makes life beautiful, isn't it? Okay, so how come they never taught this? They used those little stuff that we had over there, okay? I actually tricked you. I made that. That's not in the language. so it was like, what the hell? I'll explain. So when they designed the language, these are people who designed the C language. There are people who doesn't, before C, you're not old enough to know languages like COBOL. COBOL. Have you ever heard of it? COBOL? It's common business language, something like. It was such a, it was crazy. Language was literally in English. You had to write add 5 to, you literally, it was a bad language. So C language came right after. I said, the heck with it. We want to type the least amount of characters. We want the language to be very short so we can type quickly and write a program. So to do that, they said, instead of pointer is too long, let's put an asterisk, okay? So what happened was that the pointers that they had, they all just changed to asterisk. But remember, that asterisk doesn't belong to variable. It belongs to the type. So together, integer, pointer, and double pointer is what we have. Never ever call an asterisk that comes after a type as asterisk or star. Say it what it means. So integer, pointer, double pointer, employee pointer, okay, car pointer. Are we okay with that? Then they say address of is too long. Let's use an ampersand instead. So what you do, if you want to extract the address, you put an ampersand. And that ampersand is a unary operator that extracts the address of a variable. Are we okay with this? And because it was getting too easy, they said, let's make it a little difficult for them. So what they did, they make target of asterisk 2. So asterisk is used for target of 2, but we can recognize which one is which. How? If the target of comes before a variable name as a unary operator, that essentially means target of. Okay? So when you look at an asterisk, if you go, wow, life is beautiful, everything's good, that means it's multiplication. A multiplied by B, right? If you see there is a type and an asterisk after, it means asterisk belongs to type pointer, whatever it is. If the asterisk comes as a unary operator before a variable, it means that variable is a pointer and it means target of, right? So in writing, this is what I wrote. Target of and pointer are both presented by asterisk. If it comes after a type, it means type pointer. Like integer pointer, double pointer. Because it was C, I had to write struct, but in our case, it's employee pointer. If it comes in front of a variable as a unary operator, it means target of. A is equal to target of B. Target of T is equal to X. A is equal to B multiplied by target of C. You see something like this, you immediately know C must be a pointer. Because asterisk as a unary operator, it means that the one that comes after is a pointer. Or I can say E is equal to target of M multiplied by C multiplied by C. Are we good? All right. So, how the devil this code worked? You see that pointer.h? Let me add it here so you can see. So I literally say, any place you see target of, replace it with an asterisk. Any place you see address of, replace it with an ampersand. Any place you see pointer, replace it with an asterisk. So that is essentially what it is. What I mean, my point is, if you say it right, it's going to make sense. If you say A is equal to ampersand A, you will never ever understand what the heck is going on. You have to say B is equal to address of A, not ampersand A. Say it what it means. Are we good? Are we okay? All right. Now, another thing that is good to know is how arrays are managed, because if you're thinking pointers, you're actually thinking arrays. What they have done, we understood that we actually create an integer, it creates something like that, right? And we know I can create an integer pointer and set it and access it and so on and so forth, right? We know all these good stuff. There's no problem with this. Are we okay with this? But what happens when you create an array? When I create an array of 5 integers, it actually puts 5 integers back to back in memory, okay? Contiguous array of bytes. It's impossible for half of the array to be somewhere and the other half another way. It must be a contiguous piece of memory. Are we okay with this? All right. So we know that there is no name at the beginning, because if AR is at the beginning, AR is name of which one? So they couldn't do something like this. What they did, they said, we're going to make the array like this. So when you say integer AR5, of course, if I say AR3 is 2, 3, 4, 5, it's going to set it. We know that. But if I say AR5, this is actually what happens. It creates a constant integer pointer somewhere with the name of the array. So this line, writing it, will create 2 different things. A set of integers and 1 single pointer of the type of integer, and makes it point to the beginning of the array. That is where index 0 coming from. That's why when you say AR0, it means the first element, because it means from the address of the beginning of the array goes 0 integers further, which means the first one. If you put 1, it means go 1 integer further. It becomes the next. And that's what makes a pointer different than a regular variable. A regular variable, you add 1 to it, 1 will be added to it, right? To a pointer, you add 1, the size of the target will be added to it. So if I have a pointer of integer with 16 in it, and I do +1, it becomes 20, because an integer size is 4. It wants to go to next integer. That's the difference between a pointer and an unsigned integer. Otherwise, we could have used unsigned integer. That's the only reason for it. So anything is the size of the target. So if I actually add 2 to an integer, then 8 will be added. If I add 1 to a double, 8 will be added. If I add 2 to a double pointer, 16 will be added to it. So it can go to 2. Anyways, because of this fact, if you write target of AR is equal to 2, 3, 4, 5, actually the first element will be set. And there is absolutely no problem with that. That's why when you are passing an array to a function, you can either use array notation, which is essentially an array with no elements, which means only a pointer, right? Or you can just write a pointer. You can write integer pointer AR and then pass an array to it and treat it like an array. So not only I can use an array like this, write AR2, but I can use pointer notation, writing target of AR plus 2 is 555. So essentially it adds 2 to the address, which means goes 8 bytes further. Then I say target of, then that means it's got to be overwritten by 555. That's called pointer arithmetic. Okay? And that's the end of IPC 144 lecture for pointers. Okay? So do we know what pointers are now? Hopefully. Now I'm going to start the lecture for 345. So when we actually get to the pointers, we can actually understand what happened. We good? The slides are there, that PTR thingy is there, everything's there. I'm just going to do something in here for the name. So this pointer PTR is there, and I'm going to call this fake pointers. Okay? So you know which one we're talking about. Questions? Suggestions? Objections? All right. Let me see if I'm recording. I just want to make sure that I'm actually recording on Microsoft Teams, and also close this one. Yeah, recording and transfer. Okay, good. Everything's fine and dandy. So, now we're going to take a closer look at fundamentals. We said that every variable in C++ has a type. It tells the compiler how to interpret the bits stored in memory. That's why when you have an integer and you set it to 0, the entire for integer will be set to 0. So it actually goes through it. And what operations are allowed? This is what we call a type. So the most basic type that we have, we call it fundamental types. The very first one that we need to deal with are, obviously, integers. In here, I seriously need to add this. Just to have the emphasis that character is nothing but an integer. Okay? So when I run this program, and the postfix that you see over there, I'm adding to the literal values, forces the compiler to create that literal value of that type. So, for example, if you want a long integer, you have to put 2 L's at the end. Even if you put 0 over there, you put long L is equal to 0LL, which means the 0 that I have is going to take 8 bytes in memory. Okay? So it's not going to cast. It's going to literally create the variable that you want and the value that you want for it. Okay? So if I run the program, obviously what we are going to see will be this. And I'm going to put this one at right and this one at left. At the end of the class, tell me when is it? Sorry, I don't know why they put timer for half an hour for this thing. Anyways, too small? Let me know when it's good. Is it okay? Can you see it? Can you see it back there? The font is okay, or you want it bigger? It's good? Everybody's good. Reason is that I want it to fit, and I want the answer over there too. So as you say 65 over there is shown as A. It was 65. So, and that obviously, so if I actually say over here CH plus equal 2, and I do that C out thingy again for the character, obviously the outcome is going to be C, because it adds 2 to the ASCII code, therefore it's going to show the shape of 67. We good? Integers. Oh, C dash integers. How many fingers? 10. If I start from 0, what is the last one? 9. Are we all good with this? So if my fingers can show 10 digits, it's got to be from 0 to 9, right? Now, if I want to show negative numbers with it, I have to decide which one of these two is 0. So let's say this is 0. If this is 0, then I'm going to have minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, right? So minus 1 will be the small, minus 5 will be the smallest one, and 4 will be the bigger one, the biggest one. That's why positive numbers in variables are always 1 less than the negative numbers. When you have a character is minus 128, positive 127. When you have integers, the same thing. When you have, so that's the reason for it. You okay with this? Okay. But how can we make this from 0 to 9? That's when unsigned integers come to play. So if you make something unsigned, whoops. If you make something unsigned, all you need to do is to add unsigned at the beginning. And that makes the size 0 up to something. Okay? So that's unsigned integer. You can have unsigned character. You can have unsigned short, unsigned long, unsigned long, long. All these things work perfectly. Are we okay with this? And if you want an unsigned line, you write UL at the end. Or you write ULL at the end to make it unsigned integer, literal value. Are we okay? Yes?
Could you explain what unsigned does again? In terms of how much bytes it allocates?
The bytes are exactly the same. But because it's used, so essentially, we have a sign bit in a, there's something I think, the first semester they didn't talk about this, did they? Bit patterns and stuff, they didn't say anything. Okay, so what happens is, I don't want to go to Boolean algebra, I just want to quickly tell you what's going on. So what happens is that you have 32 bits, right? When you have 32 bits, the left bit over there is the sign bit. If the left bit is 0, it means that the other 31 is showing what the value is. Therefore, half of the size. But the first one is 0, right? When you want to make it negative, they make that one 1, and the rest becomes negative. And because you have one digit 1, the other had one digit 0, this one becomes 1 more than the others. Therefore, negative values are bigger than, like with absolute value is bigger than the other one. So when you say unsigned, it means there is no sign anymore. All 32 bits will be occupied to show the value, hence twice the size.
Because we don't need negatives.
Then you can go unsigned. Size t is essentially a type def for unsigned integer. When you write size t, there are no negative values for it.
This is the case because no negatives are being used.
Yes. What is overflow? Who has the microphone? Oh, did you answer already?
I think so, some stuff.
Take the microphone. What is overflow? When we say something overflows, what does it mean in language? Do you remember?
Yeah, it's characters are going out of the type? Like there
Uh,
are more than it can support, can fit on?
It fits it. Oh, perfect. Yeah. So essentially, when you put more in a variable than it fits, we call it an overflow. But you have to understand that variables work in a circular way. If you know Boolean algebra and how it works, it's very normal. But I'm just going to show it to you in kind of a diagram way over here to see what I'm talking about. So essentially what I'm saying is that if this is 0, okay, and this is the maximum number that it can get for positive values, and then you can go from 0 backwards and reach to negative values. It's a circular thing, which means if you go to the maximum positive and add 1 to it, it becomes the smallest negative. So if you have a character and you put 127 in it, if you add 1, it becomes minus 128. Okay? Everything is circular like that. If it's an unsigned integer, then this is what you have. You have the 0, and then it goes over here all the way to here. Okay? And that's the maximum positive. If you pass, so if I have an unsigned characters, it's from 0 to 255. If I have the 255 value in it, I add 1 to it, it becomes 0. Okay? And explanation for it is very simple, because 255 is a byte with all ones in it, right? When you add a 0 to it, 0 and 1 will be 1, 0. Carries 1, becomes 1, 0. 1, 0, 0, 0, 0, and the last one goes what we call a big pocket. It goes to garbage, and therefore everything becomes 0. Okay? Okay. Floating point type. So this is unsigned ones. This is all C, by the way. Oh, no, yeah, so floating points. This is a tricky one. Floating points is a tricky one. I have to explain. This is something that kind of a misunderstanding between the things. So floating points, first of all, variables are like this. It's kept in the computer in scientific notation, which is essentially a variable multiplied by 10 to some exponent that it has. So that's how it's kept in memory. So we have float, we have double, we have long double. Unlike integers, that when we have character, short becomes twice the size of a character, and integer becomes twice of size of a short, and we go up like that. In floating points, that's not the case. It's not the size that matters. It's the precision. That's what they say. Float, F, is single precision. Double is double precision. Long double is extra precision. Let's put it very precise. How it works. So first of all, please understand how you write the thing. So when you put a real number, 1 point something something, and you put an L at the end, that essentially means a long double. If you just put 3.1456, then that becomes a double. By default, everything is kept as double. And if you put an F at the end, then it becomes a float. Okay? So because double is the best thing to use, like it's not as precise, but it's not very bad like float, that's why standard goes by double. If you want to make it a float, you can do it that way. So how does the precision work for floating points? So when you have floating point values, they say Okay? Floats can be precise only for 7 significant digits. What does it mean? When you have numbers back to back where leading and tracing zeros do not exist. That's the precision it can take. So F1 over there is precise. It's not going to lose any value. F2 is bad because you have more than 7 digits back to back. Don't forget, like F3 over here, you see, that's safe because it's 7 digits back to back. But F4 will lose digits, will lose data. For doubles, it's 15 digits. So if you have 15 digits back to back, it's precise. The reason why F3 and F4, why F3 and F1 are the same is because the point moving in the number only changes the exponent value. The digits are what is being shown. Because 7 digits is for float, that's going to be anyway 1.23 yada yada multiplied to 10 to minus 1. But this one will be the exact same thing, 1 point something something multiplied to 10 to power minus 4. So it's the exponent of the 10 that changes when the floating point moves to left and right. That's why the leading zeros and the trailing zeros don't count. In the middle, it must be 7 significant digits. And for double is 15. For long double, I don't even remember. I think it's 386, something like that. So it's very precise. Or 100, I don't remember, quite frankly. Okay? So it's very long for long double. We good? So that's when we say it loses value. That's what I'm saying. And because of that fact, you should never, ever compare 2 double values, 2 real numbers for equality. Ever. You can never for sure. Let's say you have a logic, you have a double A and a double B. And when the logic follows, you walk through it, you are 100% sure that the value in A and B are both 2. If you write an if statement, if A is equal to B, most likely it's going to fail. Because one of them is 1.99999999999, the other one is 2.00000. The bit pattern is not the same, although the values are the same. So you never check real values. When I say real, I mean it's not scalar. It means 1 point something, the one that has partial, doubles, floating points. You never check them for equality. How you check if they are equal? First, you have to find out what is your precision in your program. Like for me, 2 variables that are 0.0001 in difference, they are equal to me. First, you find that thing. Then, to see if 2 values are the same, you reduce one by the other. Then the absolute value of the difference should be less than the difference that you want, and you're good. Okay, when I say absolute value, it means when you reduce one by the other, if it's minus 0.111111, you remove that minus. Okay, you make it positive. Anyway, so you know what. So you have to check the difference and see if the difference is less than the value, less than the precision of your, yeah. It's the exact same thing. It doesn't matter how precise it is. The fact is that one is 1.309 and the other one is 2.299 zeros and a 1 at the end. The bit pattern still is not the same, therefore they are not equal. But for all means of programming, they are equal. Okay, are we good? Okay. Okay. When C language came, everybody got, like those people who did regular programming languages, irregular other programming languages than C, they got a little freaked out. My lady, you have the microphone over there. So, what is true in C? Do you remember? When we want to check something, an if statement, what should be inside an if statement so C language decides it's true?
Like we use the Boolean for that, like if,
If you have a condition,
yeah.
what the value of that condition should be for C to say it's true?
We use like the Boolean thing.
Oh, no, you don't use Boolean. You can put if 1.956. Is that true or false?
Oh, the factorial sign?
No. Pass it. What is it?
It is 0 for false.
And anything else is true. Yeah, okay. So 0, can I have the microphone? 0 is false and anything else. Get closer to each other. It's good. So I don't have to run around. So it's going to be yours. So in C language, this is what happened. So we had 0 for false. Anything but 0 was true. And it is still the same. Absolutely no difference. But everybody freaked out. Oh my God, what are we going to do now? So in C++, they actually created a type. They called it Boolean. Okay? They called it Boolean. What is Boolean? So Boolean is essentially an integer. But the difference is that it's literally an integer. The only difference is that you put anything but 0 in it, it converts it to 1. Okay? And that gives you this. When the condition returns you truth or falsehood, it's only 0 and 1. So if you say A is equal to B less than C, if you say A is equal to B less than C, A can only be either 0 or 1. So when the result of a condition check is returned by the language, it's always 0 or 1 and nothing but that. Literally, it's a Boolean. But when a condition is being checked, 0 is false, anything but 0 is true. Hence that. So if I now execute this beautiful program of mine, you'll see that that last flag that has 1.234 in it actually will be shown over there as 1. Okay? That's what a Boolean is. Got it? Are we okay? So Boolean is a type that converts everything other than 0 to 1. We go? Okay? We already talked about character types. You know what they are. I'm just going to put it over here so we know. We know what character types are. If they have ASCII values, you cast them to an integer, the ASCII value will be shown. Okay, there's nothing extraordinary about it. You already know it. And this is what it is. Okay? Are we okay with this? All right. But I have to put it over there just to remind us. E, F, G. Void type. Void type means no value. Okay? Void type means no value. Because of that, you cannot create a variable of type void. That doesn't make sense. Like void I? It means no value. Like a variable's job is to hold a value. Therefore, you cannot create. But when you want a function to be shown that it's not returning anything, that's void. Are we okay with this? So that's a void type. C++ has introduced a new way of initialization, which is an amazing thing. Forget about equal to or what you want to put, like how you want to initialize something. First of all, what is the meaning of initialization?
When you assign a value.
Opera voice, please, opera voice, so I can hear.
When you assign a value to a variable when creating the variable.
Okay, so you saved yourself at the end. When you assign a variable at the moment of creation. So when you set some value inside a variable at the moment of creation, it's initialization, okay? Now, with respect to object orientation, when you assign an object to a value at the moment of creation, what is being called? An object, not a fundamental type. Let's say employee. You have employee. E is equal to 234. When you have something like this, initialization in object orientation is calling a
Object.
No. Pass. What is it calling?
Constructor?
Close enough. Instructor is me. That's a constructor.
Yeah, constructor.
I'm the instructor. That's a constructor. But you're close enough. Pass it. So it calls a constructor. So essentially a constructor is called for initialization. Just let's have that one. Now, you see line number 6 and 7 and 9, none of them are needed. Just put a curly bracket in front of whatever and put the value in it. It's universal. It will set it up. It does not make any difference what you have. And it's a type-safe thing. Why? Because of this. Say I have a class, student, and student has student ID, and it has GPA, okay? And it has a constructor, student, int, I'm a bad boy. STID and double GPA, okay? And that's a thing that it has, right? And let's say by default the GPA is 4.0 and the student ID by default is 0, okay? So that's so to initialize a student, I can write student S 234 and 3.5. So no more parentheses, remember that. You can use it still, but don't. Why it's type safe? This is why. You want an integer to be initialized to 0. You can write integer I, and that's it. You want a pointer to be set. You write double pointer, D, and you do that. You want a student to be defaulted. You write student, and you do that. It's all the same. The integer becomes 0, the double becomes null pointer, and the student becomes default constructor, whatever it is. Okay? Are we okay? That's universal way of initialization. So this initialization is something that you need to use from now on. You can put an assignment in front of it, but you don't need to. This is just fine. Type inference. There is something that first looks a bit useless, but later on when we talk about templates and types like that, the keyword auto becomes very useful. So I can write over here, as you see at line 7, I'm writing constant auto n is equal to 6. It takes a look at initialization and sees that that thing is being initialized to a 6. And 6 is an integer, so auto will be changing to an integer. In a loop, I'm writing for auto I is equal to 0. What does it mean? Because 0 is an integer, the I become an integer. When you are initializing, if you let it as auto, it automatically looks at the initialization and creates your variable to fit your initialization. That's called auto, okay? For a for loop, you're typing an extra character, just write int, okay? But later on you'll see when we get to templates, sometimes you don't even know what is the type of the thing that you have, and you want to create an instance out of it. If that's the case, then auto is your friend, okay? We'll come to it soon. Are we okay down to this point? All right. All right, 3:37. It's time for the quiz, okay? And the next one, so turn on all your computers, local computers, please. You have seen my whatchamacallit? Why you're shutting it down? Okay. So first let me stop the recording. You've seen my announcement about doing that. Okay. But this quiz has nothing to do with it. This quiz, you don't have a mark for it. It's just for me to know how you're doing, okay? So it's quiz 0. Have you done quiz 0 before? Have you done quiz 0 before in here?
Yeah,
So I changed it and I created a new one. If you have done it, you're doing it again. Okay, so do the usual. So let me just stop the recording.